Hey everyone, Devin here. I'd like to start today by posing a question. Everyone knows the thought experiment of if a tree falls in the forest and no one is around to hear it, does it make a sound? Well, let's mix it up a bit. How about if rain falls in the forest, but there's no way to measure it, did it ever actually rain? To answer this, I'd like to talk about two things, models and pubs. Well, not those models and pubs, but instead hydrological models and predictions in ungauged basins, pubs. Okay, so let's start with models. For the purposes of this video, I only want to talk about two main types of hydrological models, lumped models and distributed models. Let's go use my backyard as an example.
Okay, so I have this whole area back here, and let's say I want to know how much water comes out of my driveway at the end of any given storm event. So if I wanted to turn this into a lumped model, I would have to assume that everything and every variable back here is uniform. I'd have to lump it all together into one set of values. Now, this is ideal for areas where the ground doesn't really change much over any given watershed, or when you have limited computing power in order to run your models. But in highly diverse things like, say, my backyard, we have grass, we have plenty of asphalt, there's trees, there's everything. It doesn't really get the whole aspect of what this watershed would be. Now, distributed models, on the other hand, are a different beast entirely. They take your entire study area and split it up into tiny little squares called pixels, whatever size you choose. This could be 1 kilometer by 1 kilometer, 100 by 100. It could be decimal points by decimal points of actual degrees of latitude and longitude, or it could be 1 square foot. So now if I were to take this pixel and apply it everywhere over my driveway, I'd get a much clearer picture of what's coming out the back end. Now, the cool thing about using pixels is that every single pixel can have its own identity. That means its own land cover, its own soil profile, its own depth to water. Everything that you need to run a hydrologic model more successfully, you can put it in at the pixel level and then run it from there. It takes a lot more computating power because it's a much more powerful tool, but the end results that you get are astronomically better than you can get at recreating hydrologic model profiles otherwise.
So that's what models are, but what do they do? Long story short, they operate under the assumption that the water that goes into the system has to equal the water that goes out of the system. So in other words, they use a lot of equations to turn precipitation, which is your water in, into stream flow, which is your water out. This output gets measured over a set amount of time at a location of your choice, which is usually at a point in a stream where there's a gauge. So your brand new set of data now comes in the form of a hydrograph, or a visual representation of stream flow at any given time. As you work with hydrologic models, you're basically dealing with a cycle of three things: simulations, calibrations, and validations. Okay, so simulations are your meat and potatoes. They're the data that you generate naturally by running your model. You say, hey, it rained this much on this day, tell me about flow at this point, and boom, it spits out a hydrograph. But how do you know just how good your recipe is? That's where the next two steps come into play. Calibration and validation go hand in hand. Calibration is the process of fine-tuning your model's variables, and validation is the process of comparing these newly calibrated simulations to actual data. So traditionally, when you choose where to place your gauge in your model, you place it in the same location where there's a gauge in real life, because in real life, these gauges are constantly collecting streamflow data, which makes them an invaluable resource for reference against what your model is telling you. But why is this process important though? Well, the goal of running a hydrologic model is to get your hydrograph to behave as similarly as possible to your reference hydrograph, thereby allowing you to say, hey, my model represents my area extremely well. We should use it in the future when dealing with storms. You're calibrating your model by changing different variables and then validating it against your reference gauges, all while generating new simulations to continue this cycle. Now, this is all well and good, but what happens when your model processes start to break down? What if your area has poor record of rainfall? What if there's so many mountains that there's no radar data to make up for it? And what if there's no reference streamflow data because your location is ungauged? Yep, that's right. It's time to talk about pubs. Now, making hydrological predictions for ungauged basins has been growing more and more important. So much so that the International Association of Hydrological Sciences has been rallying the hydrology community to focus studies on them since all the way back in 2002. Now, despite there being nearly 31,000 strain gauges across the globe, they're only associated with roughly 58% of the land area. So with no rain gauges, no radar, and no reference gauges to calibrate your model with, how can you possibly know what's going on? So let's first focus on the issue of getting the water into our models. So what's our answer? Satellites. Oh yeah, we quite literally have the technology to measure rainfall from space. Our new best friend over these ungauged locations is the GPM constellation, the Global Precipitation Mission. Launched back in 2014, GPM's core observatory satellite is loaded with cutting-edge instrumentation that changed the game on making precipitation measurements from space. We now have the capability to know when, where, and how much it rains or snows anywhere across the globe at pixel scale. With satellite data in hand, we've now solved our water in problem, but what about our water out? Well, one solution that's currently in development involves the use of a framework that pairs our pixel-based distributed hydrologic model and our brand new pixel-based satellite data with a complex set of equations that estimate and generate parameter values, so things that you can calibrate, for every single pixel over our area based on their real-life physical characteristics. So not only does this framework automatically generate theoretical gauge locations based on the topography of the area, but actually allows us to skip the calibration step entirely and generate actual output data. But don't forget, we can't skip our third step. Validating this same method against reference data shows that it does effectively represent streamflow. So by association, it should also represent streamflow in ungauged locations. Now, this does sound very promising, but admittedly there's a long way to go in this field of research. But for now, I think we can safely say yes, it really did rain in the forest. Thank you all for watching.